This video is going to look at implicit differentiation, and that's just another strategy where we can work on different types of equations that aren't necessarily showing up how we've been seeing so far. So we want to talk about implicit versus explicit forms of equations or a function. So explicit form takes the form y equals f of x, where the output y is isolated on one side. Implicit form is y equals some equation that has f and x, where, whoa, that's quite funky there, where this other side of the equation mixes x and y. Or has higher orders of y. So higher exponents of y. And the reason that this is called an implicit form is because it's implied that there's a function here. We don't necessarily see it, we don't necessarily know it, but it's implied. So an example of this where we can kind of see that, implicit form would be x squared plus y squared equals 25. So in this case, it's not y equals something. It's implied that we could solve this for y equals something. That's why it's implicit form of the function, but it's not already written in that. So the only time you have explicit form is just y equals, and then only x things and constants on the other side. Another example would be y squared equals 5 minus x, again because we have this squared here. Another form might be y equals 3y plus 2x. This is also implicit because we have y's on both sides. This one's kind of a more trivial one because you can easily see how this would be quick to solve for the explicit form, but as it stands, it is technically in implicit form. You could also have something like sine of y equals 5x. This is also in implicit form because we have things that are not just y equals. We've got something else there. So I guess this equation here is a little bit misleading, but you kind of get the idea of if it's not just y equals and then a bunch of stuff with x, it's in implicit form. So if we want to differentiate those functions, there's a trick that we can do with implicit differentiation. So implicit differentiation allows us to calculate the derivatives of, as you would guess, implicit functions. Or I guess actually the way this sentence is worded, it's going to be derivatives in implicit form. Just checking how I've written this in the notes. And one thing that they're assuming is that the function y of f of x, y is differentiable. And that should actually just be y of f of x. So it's assuming that whatever the implied function is differentiable. And we're always going to work with this assumption, so you don't really need to worry about the fact that we are technically assuming something. That's just me laying some background math stuff that might come up in your future courses. So what does implicit differentiation look like? What you're going to do is you're going to use your derivative rules to derive both sides of the equation. So you're going to have something something equals something something. Now we've implied that y is a function of x. And so because of that, the derivative of y is going to be equal to dy by dx, or alternatively y prime. So when you come to actually doing the derivative, you just need to remember that y isn't like x, where it's just going to go away when you take the derivative of it. Instead, you're going to be left with this derivative that we don't know, that we're actually trying to solve. After we take the derivative of both sides, then we're going to isolate the y prime, because that's what we're trying to solve for, or the dy by dx if you prefer using that notation. So what you're going to do is place all the terms with y prime on one side, and then everything without y prime on the other side. On the side with the y prime, factor that out, and then divide both sides by the leftover of the factoring step. This is kind of maybe nebulous at the moment, but in the next video we'll look at some examples so you can jump over to there.